this force per unit length we have calculated in the last class. Oh, hello Nawal, how are you? So force per unit length, mu 0 divided by 4 pi 2 times of I1 into I2 divided by A. This is the formula. Force per unit length of the any of the conductor you will calculate, then you will get the same formula. Okay. Wire 2. For wire 1, the formula will remain same. Mu 0 divided by 4 pi means if someone is asking the 4 per unit length of any of the two wire, then you will say mu 0 divided by 4 pi 2 I1 I2 divided by A. Okay. So this you should know. And if there is a same current in the two conductors, then both the conductors will attract each other. And if the current in the one conductor is in this direction, another conductor is in this direction, then both the conductors will repel. So I will discuss this. We'll solve one question. Find the net force on wire EB in shape of semicircle so here is one wire given, semicircular wire is there, AB, and suppose capital I is the current in this wire and capital R is the radius of this semicircle. We have to find the net force on the wire AB, that is semicircular wire. So in the last class, I have told you one formula, force on a current carrying wire in a magnetic field. And this wire is in the magnetic field and that magnetic field is in the inward direction. This is your magnetic field in the inward direction. So force on a current carrying wire is given by force current in the wire L cross B. L cross B. Both of you getting my voice?
Yes, sir. Yes, sir.
So in the last class, we have discussed this. So I am discussing the question on this formula. This is the final formula we got. IBL sin theta means if there is a current carrying wire, this is a wire, okay, having the current I, and this wire is placed in the magnetic field B, then the force on this wire will be F is equal to, in vector form, the formula is current in the wire, length vector of the wire cross B vector, okay, length vector in cross B vector, and in the scalar form, we can write IBL sin theta. And this formula is for the straight wire. Now, if you will use this formula for the semicircular wire or for some loop and for any other type of wire, then in that case, what you will do? Like here, in this case, the length, this length just open this and write this formula in the scalar form. That is ILV sine theta, and theta is the angle between the length vector and the magnetic field vector. Theta is the angle between the length vector and the magnetic field vector. So here the length in this case, this is not a straight wire. So in this case, you will take the length as the displacement length. Now, what is displacement length? Displacement length is simply the displacement. You are going from A to B. So this is the original length of the wire. But in this formula, you will put the displacement length. Displacement length is this length, AB. Means this R plus R. This length you will put. Means 2R. Okay. So finally, you will get the force I. Instead of this length, you will take the displacement length. Displacement means the distance between the initial point and the final point. So this is the diameter of the semicircular wire, that is 2R. So here you will write 2R into magnetic field B, and theta is 90 degree, because your length direction is this. Your length vector is in this direction, and your magnetic field will be inwards. Your magnetic field is inwards. Inwards means minus k cap. So theta will become 90 degree. So you will put here sine 90. Sine 90 is equal to 1. So finally you will get this answer. 2 into IR into B. This is your final answer. Theta is 90. Theta is 90. What is the theta? Theta is the angle between the length vector and the magnetic field vector. Now here in this case, your length vector is this. Okay, this is your length vector. So this is along the positive x-axis. This length vector is along positive x-axis, and the magnetic field is towards the inwards. Okay. So angle between the magnetic field and the length vector will be 90 degree. Now, if the question is like this, a current carrying coil is given. This is a current carrying coil. In this, current I is flowing. Capital I is the current flowing in this coil. This is a coil, COIL coil, rectangular coil you can see. So, and this coil is in the inverse magnetic field. This coil is present in the inward magnetic field. And current flowing in this coil is I. We have to find the total force on this coil. Total force on this coil. So you can just divide this coil into 4 parts. First part is this wire. This coil is made up of 4 wires. One wire is this, another is this, and this. 4 wires. So when you will add the force on this force wire vectorically, then you will get the answer. But what you will do? You will take the displacement length for calculating the force. Okay. We'll apply this formula simply. F is equal to ILV sine theta. ILV sine theta. And L is your displacement length. So in this case, what will be the displacement length? This is a closed loop. In case of closed loop, the displacement length will be 0. Okay. Displacement length will be 0. This is your displacement length. Is equal to 0. So your force will become also 0. I into 0 into V sine theta. So your force will also be So force on the closed loop carrying current, magnetic force on the closed loop carrying current is zero. If the coil is given like this form, and in this coil, this is a triangular coil, current is I flowing, I current is flowing in this coil like this, and you want to find the net force, and this coil is in the magnetic field. Suppose outward magnetic field is present, so the net force on this coil also will be zero, because this is a closed loop, and for the closed loop the displacement length will be zero. The force will be zero because displacement length equal to zero. So note down this point. If uniform magnetic field is there, then net force on closed loop in the next derivation I will prove this. Closed loop is zero. Okay, note it down. In the next derivation, I will prove that in a closed loop or a closed wire, the net magnetic force will be zero. Done, Nafisa?
Yes, sir.
Done?
Yes, sir. Finish.
And next topic is the magnetic movement. So for the magnetic moment, you can say, suppose you have a closed wire. You have a closed wire means this type of wire, wire in the shape of square, wire in the shape of the rectangle, in the shape of the triangle. So you have a closed current carrying wire. That closed current carrying wire will behave as the magnet. Okay. And if you will take the circular wire like this, next topic is this magnetic moment. So magnetic dipole moment for current loop. Current loop means a wire of having closed loop. Current carrying loop behaves as magnet. Current carrying loop means this is the loop or this is a semicircular wire. So here, if the current direction is this, then in this wire, this is a semicircular wire. If in this wire the current is in this direction, okay, and clockwise current, then this face of the coil, this face of the coil or the loop will behave as a south pole, will behave as a south pole. Okay, and if the current in this closed wire or semicircular wire is anti-clockwise like this, then this face of the coil will behave as the north pole. And this is for just you can remember how to decide the direction when the south pole is given. Okay, if the south pole is given, write S and write this arrow, then you will say that the current will be anti-clockwise. Okay. Current is anti-clockwise current, then face will behave as south pole. Anti-clockwise, then the face of the coil will behave as north pole. Now we will write the formula for what is the means how we will calculate the magnetic moment. How we will calculate the magnetic moment. So suppose you have this coil, you have this coil, circular coil, and this coil have the current I, and N is the number of turns in this coil. Okay, this is only one turn shown here, but if there are N number of turns are there in this coil. A is the area of the coil, A is the area of the coil, I is the current in the coil. Then the magnetic moment is given as N into I into A. Okay, magnetic moment is given by NIA in the vector form. So you can say, you can convert this area into the area vector. Okay, so here this A vector means area vector. You can write this is in the scalar form, M is equal to NI into A. Simply. So magnetic moment of a circular coil is equal to number of turns in the coil, current flowing in the coils into area of the coil. So this magnetic moment is the vector quantity. Magnetic moment is a vector quantity. And if you want to find the direction of the magnetic moment, then what you will do, you will just curl your finger along the sense of current, curl your finger along the sense of current. The direction of the thumb will give you the direction of the magnetic moment. So when you will curl your finger along the direction of the current, then your thumb will be away from you, means inward. This magnetic moment will be inward here. So direction perpendicular to the plane of the coil. Okay, so this is the plane of the coil and this coil is in the xy plane. So the magnetic moment will be along the z axis. So you can find the direction with this. Curl your finger along the sense of current. The thumb will give you the direction of the magnetic moment. Okay. So this is all about the magnetic movement. So if you have a, suppose you have this means this type of coil, and in this coil, suppose there is a current I. This is a coil in the form of the square, and in this the current is I. So the magnetic moment will be number of turns in this current flowing I into area. This time area will be changed. Area of a square will be there. So M is equal to NIA. Simple. Okay. Remember this and this. Both are very, very important. When we will study the electromagnetic induction, this thing will be required there. So just note it down. So you have to remember this point that if there is a closed wire, okay, or a closed loop in the form of wire, then if there is a current in that, that will behave as a magnet, and having the magnetic moment NIA. Note down this, both of you. This is known as magnetic moment or the magnetic dipole moment. Hello Matthew, how are you?
Good evening, sir. Sorry I'm late. I had
Okay.
exam today and had like I was sleeping. I would got
Okay,
it.
no problem. Fine. So I am discussing the magnetic dipole moment or the magnetic moment for the current loop. Okay.
Okay, sir.
So just I am just explaining it once, then you will know.
All right, sir.
So the always if you have a loop, suppose this is a loop in the form of the circle. So current is flowing in this. Okay. Suppose I is the current is flowing like this. So this will behave as a magnet, and if the current is the clockwise, then this face of the coil will be the south pole, will behave as a south pole. And if the current is anti-clockwise, the face will behave as a north pole. Now, what is the magnetic moment? So this is the circular coil and having a current I, and N is the number of turns of the coil, A is the area of the coil, I is the current flowing in it. Then the magnetic moment will be given by M is equal to Ni into A. A will be the area vector here, and in the scalar form you can write simply M is equal to Nia. And when you want to find the direction of the magnetic moment, curl your finger along the sense of current. Thumb will give you the direction. So here, when you will do this, you will get the direction inwards. Okay, and this is the direction perpendicular direction of the magnetic moment. Magnetic moment will always be the perpendicular to the plane of the coil. Okay, suppose if the coil is in the xy plane, then your magnetic moment will be along the z axis. Okay, and this is given by right hand thumb rule. Curl your finger along the sense of current. The thumb will give the direction of the magnetic. Just note it down. So Matthew, how was your paper? How was your exam?
It was a bit hard, but yeah, I did it well. I did it right. Okay.
When completed, ask me to score. Scroll down.
1 second, sir. Wait.
Okay. Current carrying, remember this point, current carrying loop means a wire in the form of like closed wire will behave as a magnet. So, and you are just watching this face of this coil from this side, from your screen, and here is the current in the clockwise direction. When you will see this uh, coil from here, okay, then it will look like that the current will be in anti-clockwise direction. From here means behind the face of this coil. Suppose this is a current carrying loop. Okay, this is a current carrying loop. In this, for me, I am watching this from here. So it is looking like that the current is the clockwise, but someone is watching from this side. Okay, it will look like the current will be anti-clockwise. So there is a dipole. If this phase is will behave as a means for the current coil carrying coil, if this phase will behave as a south pole for you, then this phase will behave as a north pole. So magnetic loop or sorry, current loop will have dipole, north pole and south pole. That is why this will behave as a magnet. So remember this point. Both of these.
Done, sir.
This cross represents the inward direction of the magnetic movement given by the right hand thumb rule. Scroll down. Matthew.
Yes, sir.
If your current carrying loop in this form, the form of rectangle, square, triangle, then also the magnetic moment will be N into I into T. Completed?
Yes,
Nawal
sir.
completed? Nawal completed?
Yes, sir.
Matthew? Done?
Yeah, so yeah.
So now see, this formula you should know. What is the magnetic moment? You should know the main thing. This formula. This formula you should know. And the direction, how to calculate the direction of the magnetic moment. Curl your finger along the sense of the current. The direction of the thumb will give you the direction of the magnetic moment. Two things are very, very important. So now we will calculate the magnetic moment of electron moving in an atom. See this. Magnetic dipole moment, or you can say magnetic moment due to a revolving electron. We know that in an atom, I am taking hydrogen like atom. Hydrogen like atom means in hydrogen one electron is there. So hydrogen like atom means there is only one electron in the atom. This is nucleus. An electron revolves around the nucleus in the circular orbit. So suppose initially the electron is here. I am supposing the electron, and this r is the radius of the path. So electron will move in a circular path like this. So suppose initially the electron is here. So the direction of the velocity of the electron will be tangential. Okay. The direction of the velocity will be tangent to the circle or to the path followed by the electron. Here also, if the electron is here, so direction of the velocity will be tangential like this. You will draw the tangent from this point. If the electron is here, the velocity is in this direction. If the electron is here, the velocity is in this direction. This you will get by drawing the tangent at that point. And this NU represents the nucleus. Nucleus is in the center. So electron is revolving like this. And R is the radius of the path or radius of the circular path. Time period. What is time period? Time period is means time taken by the electron to complete one circle. Means electron is moving from here to here, like this, like this, like this. Finally, the electron is here. So in this motion, time taken by the electron is t, and E is the charge on the electron. E is the charge on the electron. So how we will calculate the current? If electron is a charged particle, and whenever the charged particle is in motion, then there will be the current generated. Okay, so current will be charge divided by the time. Current is equal to charge divided by time. Charge here is E. Time is the time period. Time is the time period. I am taking the time period T. Now we will calculate this time period. We know that speed is equal to distance upon time. Speed is equal to distance upon time. Speed is v here. Distance 2 pi into capital R. Time is the time period. What distance the electron is covering in the time period T? It is 2 pi r distance. Okay. 2 pi r distance. This distance is the perimeter of the circle. Okay. In completing the electron is completing one circle, means the electron is moving a distance of 2 pi r. So time period you can calculate from here. T is equal to 2 pi into r divided by v. So now put the value of time period here. So you will get I is equal to T 2 pi r divided by. So you will have the current E into V divided by 2 pi. What is V here? V is the speed of electron, or you can say speed of speed and velocity have some difference. Speed is only the magnitude, velocity is magnitude, speed with direction. Okay. So here the direction at every point of the velocity is changing, but the magnitude of the velocity, that is speed, is not changing. So this is the current produced. This will be the current produced. Now what will the magnetic moment? Magnetic moment is equal to IA. I am not taking n because n is 1. When the electron will revolve like this for the one time period, okay, so n will become 1. So magnetic moment is equal to NIA. So here n is equal to 1. So the magnetic moment by the electron will be IA simply. But the electron is moving for the one time period, IA. So current, put the value of current. M is equal to this I. Put this value instead of I. EV divided by 2 pi r. Area is pi r square. Area is pi r square. And the direction of the current, as the electron is moving in this direction, electron is moving in this direction, the direction of current will be this. The direction of the current will be opposite to the motion of the electron. So you can consider this as a current carrying coil. You can consider this as a current carrying coil. Okay, I is the current in this coil, circular coil. So you will, and we know that the circular coil will behave as a magnet and have the movement, magnetic movement NIA. So this coil have the one turn. If you are assuming this as a coil, this has a one turn, so n equal to 1 you will put here, and you will have I into A. So current is this, and area of this coil, if you are considering this as a circular coil, so area will be pi r square, area of the circle. So r and r will be cancel out. So finally you have, and this pi and pi will also be cancelled out. Okay. So magnetic moment by the electron is equal to EVR divided by 2. This is the magnetic moment of electron. And for the direction, what you will do? The direction of the current is this. Curl your finger along the sense of current. Curl your finger along the sense of current. So tell me what direction you are getting, Nafisa. What direction of the magnetic moment you will get if your current is in this direction by the right hand rule. Just curl your finger along the sense of current. See where
Towards
your
us.
no. This is the direction of the current. Your thumb will be towards means away from you. Do it, Matthew. You also, and Nawal, you also. Okay, just
Away from us.
yeah, because you will your current is in this direction,
Yes, sir.
and you will curl your fingers like this, and your thumb will go away from you. So direction of the magnetic movement you will get will be inwards. Suppose if the current is like this. Is the point? If the current is like this, I is the current flowing in this direction. Now, what will be the direction of the magnetic moment? Direction of the magnetic moment. Tell me, Matthew. What will be the direction of the magnetic moment here? Just curl your finger along the sense of current.
It'll be away from the circle.
No. Nawal, you tell. Direction of the magnetic moment. for this coil. Just curl your finger along the sense of current. See where your thumb is going.
Inwards.
Do this by yourself. This current is in this direction. So curl your fingers like this way. So your thumb will be towards you, means outwards. Okay.
So I didn't understand.
Okay. Just see. When you will curl your fingers like this, so your thumb will be like this towards you.
Oh, okay.
See,
Yeah.
where your thumb is going.
But sir, you have to curl it in the direction of the
Actually,
field, right?
you have to curl your finger along the sense of current, clockwise or anti-clockwise. Okay. See here, just a minute. This current is anti-clockwise now. So
Yeah.
curl your these 4 fingers anti-clockwise and see where your thumb is going. Thumb will be towards you. And if your current is in this direction, I am taking one more example. Suppose this is your point, and the direction of the current is in this direction. This is clockwise direction. So now, accordingly, you can just imagine this. You are just holding this coil in the sense of current. You are holding this coil in the sense of current. Okay. Try to hold this like this. Means curl your finger along the direction of the current. Here current is anti-clockwise. Then your thumb will be away from you.
Okay. I understand, sir. Yeah.
Here the direction
Because
of the
what I
magnet.
thought was you had to put a hand through on the loop.
No, on the loop, no. Actually, what you are using first your these 4 fingers. You are just curling your four fingers, and automatically the thumb will give you the direction. Don't think like that. You should think like this. That now you will curl your 4 fingers in the along the sense of the current. Current can be like this or current can be like this. If the current can be like this, your thumb will be outward. If the current will like this, then your thumb will be towards you. So in this case, the direction of the magnetic movement will be inwards. In this case, the magnetic movement will be outwards. Okay. Now got it, all of you, Nafisa and Nawal?
Yes, sir.
Yes, sir.
Yes, sir.
This is not that tough. Means now I will use a one term, angular momentum. Angular momentum. So, do anyone know what is angular momentum?
When a particle goes on a circular way, the momentum experienced by that at a particular angle theta is the angular momentum.
Anyone else? Angular momentum, like you have in a linear motion, when you are moving along this straight line, or in a translational motion, you have a momentum. Like in a circular motion or rotational motion, there's a term angular momentum. And angular momentum, suppose I will explain this angular momentum with the help of this example. See this. Here is one mass, and this mass is moving on a circle. This mass is moving on a circle, and this mass have the speed v. Okay. And direction of the velocity will be in this direction. This mass have the velocity v, or you can say speed also. So this direction of the velocity will be tangential to the motion. Suppose if your electron is, if your mass is here, in that case, the speed will be in this direction, or the velocity will be in this direction. If your mass is here, then in that case, the velocity will be in this direction. Tangent, you will draw the tangent from this point and you will get the direction of the velocity. So angular momentum is represented by L. This angular momentum is a vector quantity. The magnitude of the angular momentum is given by momentum into R. You can say mv into R. This is your angular momentum. Mass into velocity into radius. Okay. Here R, capital R you will put it. M is the mass, V into R. This is your angular momentum. And mb, I have told you the linear momentum. Formula of the linear momentum P is equal to mass into velocity. Okay, note it down. Note down this. Whenever a particle is moving in a circular path, the direction of the velocity of that particle will always be tangential to the circle.
So you can scroll down.
Nafisa, should I scroll down? Return. Nafisa, are you getting my voice? Okay, right. Nafisa, are you getting my voice?
Yes, sir.
Have you written this?
Sir, did you say something?
I am saying that you have you completed this or not? This part
Yes, sir.
completed now? Write down this.
Yes.
Done, sir.
So here, just wait. I am changing it. You can suppose this has an electron. Okay, here is here is electron, and this electron is moving in the circular path. So the angular momentum of electron will be mvr. mvr is the radius of the circle. Okay, you can remove this linear momentum because I have already discussed what is linear momentum. So angular momentum of the electron moving in the circular path will be mass of the electron, velocity of the electron into the radius of the circular path. Okay. Write down this part. There is a relation between the angular momentum and the magnetic moment. Relation with the orbital angular momentum and the magnetic moment. So now we will discuss what will be the ratio of m divided by L. So put the value of m for the electron we are calculating. Okay. For the electron, what is m by L? So m magnetic moment for the electron moving in a circular path is equal to ev into r by 2. ev r by 2, and here you will put, for the L you will put mvr. You will put mv and r. This v and r and this v and r will be cancelled out. Okay. So finally you will get m by L ratio of magnetic moment divided by the angular momentum of the electron is equal to E divided by 2m. E divided by 2m. E is the charge of electron, m is the mass of the electron. Now, according to this, there is a relation between the magnetic moment and the angular momentum of electron. Okay. So now, Bohr's model. So Bohr is a name of the scientist. Okay. So according to this, the orbital angular momentum or the angular momentum of an electron is an integral multiple of h upon 2 pi. Integral multiple of h upon 2 pi. H represents the Planck's constant. Planck was the scientist, and here E is the charge on electron, that is 1.6 into 10 to the power minus 19 coulomb. The value of the Planck constant is given by 6.626 into 10 to the power minus 34 joule per second. Mass on electron is 9.1 into 10 to the power minus 31 kg. So angular momentum of electron is integral multiple of h upon 2 pi. So here n can be 1, 2, 3. Integral multiple means the n can be 1, 2, 3, 4, 5 like this. N can be the integer. N will be the integers. Okay. So this is. So from this L, you can calculate the M, okay, by using this relation. So M you can calculate from here. M is equal to L into E by 2M. So L is equal to N H divided by 2 pi. This is E by 2M. Finally, you have NHE divided by 4 pi M. Will be the magnetic moment. So magnetic moment is given by NHE divided by 4 pi M. This is your magnetic moment. And if you are putting N is equal to 1, then you will get HE divided by 4 pi M. And this quantity is known as Bohr's magneton. In examination, the examiner can ask you what is Bohr's magneton. So you will write first this formula, or you can say this is the magnetic moment for n is equal to 1. And what is this n represents? N represents the shell. K shell, L shell, M shell. There are shells inside the atom. For K, n equal to 1. For L, n equal to 2. Have you completed this, Matthew? This thing?
Yeah, sir. Yeah.
No. The orbital angular momentum of electron is integral multiple of h upon 2 pi. This is angular momentum L.
Done, sir.
And if you will put if you will put n is equal to 1, then you will get this magnetic moment as minimum. Okay, because minimum value of n is 1. So this is also the minimum magnetic moment. Minimum magnetic moment of electron.
Done, sir.
Okay, all of you completed, Nafisa and Nawal?
Yes,
Yes,
Complete.
sir.
So this is all about when the electron is revolving around the nucleus. We have calculated the magnetic moment in this case. We have calculated the angular momentum. We have calculated the ratio of the magnetic moment and the angular momentum. And there is a relation between the angular momentum and the magnetic moment. And according to the Bohr's model, the orbital angular momentum of the electron is integral multiple of h upon 2 pi. And Bohr's magneton is when you will put n is equal to 1, then you will get the minimum magnetic moment of the electron. That minimum magnetic moment of the electron is known as Bohr's magneton. Okay. Now we will discuss torque on a current carrying coil. So for before this, you should know what will be the magnetic force when a current carrying wire. This is a wire carrying a current of length L is placed in the uniform magnetic field, and that magnetic field is making an angle theta with the length of the wire. In the vector form, this is given as force vector is equal to I into L cross B. In the scalar form, this is given by IBL sine theta. Theta is the angle between the magnetic field and the length of the wire. And here, force, current, and the magnetic field, three of these are mutually perpendicular. Mutually perpendicular means F is perpendicular to I is perpendicular to B, and B is perpendicular to F. And we have to calculate the torque. And how the torque will be generated on this, we will see. This is a current carrying coil. ABCD is a current carrying coil or current carrying loop, you can say. And this is the magnetic field. Magnetic field is in this direction, and this is the plane of the coil. Okay, this is the plane of the coil. So the plane of the coil is making an angle theta with the magnetic field, and L is the length. Okay, this is a rectangular coil. L is the length, B is the breadth of the coil. So this is the magnetic field making an angle theta with the plane of the coil. So you can divide this coil in the form of 4 wires: wire AB, BC, CD, and DA. This coil is made up of 4 wires AB. For analyzing the force, what you will do, you will divide this into 4 wires: AB, BC, CD, and DA. And for AB, there will be some force. For BC, there will be some force. For CD wire, there will be some force. For DA wire, there will be some force. When we will combine all the forces, means when we will add all the forces vectorically, then we will get the net force on this current carrying coil. So this is a condition like here AB. See this AB only. So AB is like the current carrying wire in the magnetic field. BC is like the current carrying wire in the magnetic field. CD is the current carrying wire in the magnetic field. DA is the current carrying wire in the magnetic field. So we will use this formula. So when you will calculate the total force on the coil, total force on the coil A, B, C. Total force will be the force on AB wire, BC wire, CD wire, and DA wire. So you can write total force is equal to FAB vector plus FBC plus FCD plus FDA. Now we will apply this formula. Okay, we will apply this formula. Now force on the wire AB. Force on the wire AB means see this wire, and this wire is in the magnetic field B. So what will be the magnetic force? IBL sine theta. IBL sine theta. So current is I, magnetic field is B, length of this AB. What is the length of this AB? B. Small b is the length of this AB. And sine of theta. Is it or not? Now, what will be the direction of the force on the wire AB? See, this is given by the right hand rule. This is given by the and also the force on the wire will be perpendicular to length AB. In the last class, I have discussed here. This. This case I have discussed. Force on a current carrying wire IVL sine theta and direction. Point your fingers in the direction of the current and curl towards the magnetic field. Thumb will give the direction of the magnetic force. So we are using this. So total force on the wire will be vector summation of all the forces on the AB wire, BC wire, CD and DA wire. All of you getting or not till here? Matthew, clear?
Yes, yeah.
Yes,
This is
sir.
because we are dividing this coil into the 4 wire and we are calculating. Now we have just calculated the magnitude. Now we will convert this in the vector form by multiplying this with the unit vector. So for the direction of the force, so how you will calculate the direction of the force on this wire AB? You will point your finger in the direction of the current. So this coil is like this. This coil is like this. Suppose the magnetic field in this direction along the x-axis. Suppose this is the x-axis direction. You have to imagine this. And this coil is like this, and now this coil is rotated like this. And this is the direction of the magnetic field. This is a coil, and this is the direction of the magnetic field. See here. Okay, see. This is the magnetic field, and this is the coil, plane of the coil. Both are making an angle of theta. Now put your 4 fingers along the direction of the current and curl it towards the magnetic field. So do this by yourself. This is the direction of the current, and when you will curl it toward the magnetic field like this, you will get the direction of force along the positive y-axis. Direction of the force will be along the positive y-axis. This is the direction of the force on the wire AB. So force on this wire AB along the positive y-axis means J cap. So you will multiply this with J cap. Now for the wire, I am removing this now. For this wire BC, the direction of the force will be given by the right hand rule. So see this length of the wire is in y-axis, and this magnetic field is along x-axis, and length and magnetic field and the force are mutually perpendicular. So definitely the force will be along the z-axis. Z-axis means inwards or outwards. Inwards or outwards we will decide with the right hand rule. So place your fingers along the direction of the current and curl it towards the magnetic field. Okay, like this. This is your direction of the current, like this, and your magnetic field is like this. You will curl it like this. You will get the direction towards yourself for this wire. Just calculate this first for this wire. Put your fingers for this wire AD. Put your four fingers along the direction of the current. This is the direction of the current, and magnetic, and curl towards the magnetic field. Okay, curl towards the magnetic field. Magnetic field is in this direction. Okay, so in this direction, this is the direction of the magnetic field. When you will curl it, the force will be inwards. Okay, so on this wire AD, the force will be inwards. Force on wire AD will be inwards, means minus K cap, and on this wire the force will be outwards, that is FBC. This will be K cap, and here when you will calculate, you will get the downwards. Along the negative y-axis you will get the force. CD minus G cap. Now you can write all these forces into the vector form. F of BC, this will be again I into magnetic field. Length of wire BC is L. Okay, L, and sine theta, and here that this length means here the magnetic field will be perpendicular to the length of this wire. Here the magnetic field will be perpendicular to this length. So here the sine theta will be sine 90. So I am writing this for this BC wire. For BC wire, the magnetic field will be perpendicular. Okay. So sine 90 you can write here, and you will multiply it with a K cap. Okay. Now for CD, see this CD. Same formula will be applied. IBL sine theta. Current is I in the wire CD. Now see this wire CD. Magnetic field is constant or uniform, that is B. Length of CD is small b, and sine theta. Because this wire makes a length of this wire making an angle of theta with the magnetic field. We will multiply this with minus J cap. For the wire DA, again you will apply IBL sine theta. Current is I, magnetic field is V, L, length of the wire is L, and sine theta. This wire also will making an angle of 90 degree with the magnetic field. Okay, AD wire. So sine theta will be sine 90, and sine 90 is 1. So you will write I into magnetic field into L into sine 90, and you will multiply this with the unit vector of minus of K cap. Now see this, all the terms here. This is IB capital B into V small b sine theta into J cap. This is I capital B into small b sine theta into minus J cap. This term will be cancelled out with this term, and see this I into capital B into L into sine 90 into K cap. I B L sine 90 to minus K cap. This will be cancelled out with this. So your force on the coil ABCD will be 0. That is why I was saying that force on a current carrying loop in a magnetic field is 0. So here the total force on this current carrying loop or current carrying coil is 0. When you will apply this formula and when you will apply the right hand thumb rule, place your fingers along the direction of the current and curl your fingers towards the magnetic field, then you will get the direction of the magnetic force. So here the magnetic force is 0. Magnetic force is 0. So already we have written, but writing it again. Force on a current carrying coil. Force on a current carrying coil is 0. Force is 0, but torque will not be 0. Why? See, 4 forces are acting on this coil. 4 forces. This. And this force are collinear. FAB and FCD are collinear forces. Collinear means these forces are acting on the same line. When you will join the line of action of these two forces will be collinear. Okay, these collinear forces will not contribute to the torque. Torque will be only there when the forces are not non-collinear. Okay, torque means one force you will apply in this direction, another force you will apply in this direction, then only this will rotate. Okay, if your force, both the forces are acting, means one force is acting in this direction, this is the coil, one force is acting in this direction, another force is acting in this direction, so there will be no torque. Torque means rotation. And if you will, your line of action of both the force will not be same, then only the torque will be generated like this. One force is in this direction and another force should be in this direction. So that is why this coil, you can, if you are imagining this as a coil, this thing will rotate. So here in this case, this FAB and FCD will not contribute to torque. FAB and FCD are collinear. Collinear forces, so they will not contribute to torque. Torque. But these forces, see here, one force is along, one force is outwards, another force is inwards. Okay? One force is outward, another is inwards, and the line of action of these forces is not same. Okay, so these BC and AD, FBC and AD will contribute to the torque. So FBC and FAD are non-collinear forces, and they will contribute to the torque. They will produce torque. And what is torque? Torque is force into perpendicular distance from the axis of rotation. So now see this. I am just drawing both the forces and I am showing here. This is the length, means the breadth of the coil. This, okay, and force is acting like this and this. I am showing it here. So this will be like this. The system will look like this. Here is one force, that is F TA, and here is another force, that is FBC. And this is the point along which coil is rotating. Okay, this coil is rotating, and this distance is B by 2, and this distance is also B by 2 because this length is B. Okay, and this here is the axis of rotation. So here this distance is B by 2, this distance is B by 2, and this angle is theta. You can write B by 2 here. So this angle is theta. I have shown these two forces and this length V. Okay, when you will join this, you will get this length V. Now torque is force into perpendicular distance, this distance. Okay, force into perpendicular distance from the axis of rotation. This is the axis of rotation and this is the perpendicular distance. And this distance will be B by 2 into cos theta. Okay, this distance will be B by 2 cos theta. This distance also will be B by 2 cos theta. This angle is theta. This angle is theta. So this will become B by 2 cos theta. This will become B by 2 into cos theta. You can calculate this B by 2 cos theta with the help of triangle. Okay. This is the triangle. No? This is the angle theta. This is given as B by 2. See this triangle, how this length is B by 2 cos theta. Okay. See this triangle. Very simple. So this is the angle theta. So with respect to this angle, this side will be perpendicular and this side will be base. This side will be base. Okay. So this is base and this will be perpendicular. Suppose this is P is the perpendicular. What is cos theta? Base by hypotenuse, and this angle is 90 degrees. So this will be your hypotenuse. So base by hypotenuse. So cos theta is equal to base is this B by 2 cos theta that we have found base. Hypotenuse is B by 2. So your base will be B by 2 cos theta. That is why I have written B by 2 cos theta. Now, what will be the total torque? The total torque tau. Tau is the symbol of the torque. Total torque will be given by force into perpendicular distance, means FDA into B by 2 cos theta. What is FDA? FdA into V by 2 cos theta, and this torque will be clockwise. Okay, this torque will be clockwise. If you want to find the direction, then you can find with the help of cross product. Okay, so this torque will be, this force also try to rotate the coil in this direction. This torque will also try to rotate the coil in this direction. So both the torque will be added up. So F, due to this force BC, the torque will be FBC into V by 2 cos theta, and FDA on this wire DA. The force will be IBL on this wire. FDA will be IBL. See this part, FDA. This is DA. So the force, the magnitude of the force is this, IBL sin 90. So put this value here, IBL sin 90 into V by 2 cos theta, plus here also the force will be IBL sin 90 into V by 2 cos theta. So sin 90 is 1. So IBL into V by 2, and V by 2 and V by 2 will be V. Okay. So your formula of the torque, you will get this torque. Torque is equal to I into magnetic field into length into V into cos theta. Length into breadth is equal to area of the coil. So you will have this I into magnetic field into area into cos theta. Or you can write this formula in the form of the magnetic moment. Torque is equal to I into A into B into cos of theta. And IA is equal to the magnetic moment of the coil. So you can write torque is equal to IA is the magnetic moment into the magnetic field into cos theta. So this is your final torque. And theta is the angle between the magnetic field and the plane of the coil. This is your theta. So I am writing theta here. Angle between the magnetic field and plane of coil. This is your torque. Now, in terms of the magnetic moment, what will be the magnetic moment of this coil? Okay. This coil is like this. For the magnetic moment, you can say magnetic moment is perpendicular to plane of the coil. I have told you this already. Magnetic moment is perpendicular to the plane of the coil. So see now. This is your coil ABCD, and your magnetic field is in this direction. This is the direction of the magnetic field. And magnetic movement will always be perpendicular to the coil. This is the direction of the magnetic movement. This this. So this is the magnetic field, and this is your magnetic moment, and this magnetic moment will be perpendicular. This is your magnetic field, this is your magnetic moment, and this magnetic moment is making an angle of 90 degree with the plane of the coil, because magnetic moment is always perpendicular to the plane of the coil, and this magnetic field is making an angle theta. This magnetic field is making an angle theta with the coil, so the angle will be the magnetic moment and the magnetic field will be 90 minus theta, because this whole angle is 90 and this angle is theta, so this angle will be 90 minus theta. Okay, so you can convert the equation of the torque. Torque is given by mv cos theta, so you can write I am supposing this angle as alpha, and this alpha is the 90 minus theta we know. Okay, so you can write theta plus alpha is equal to 90 degree, and alpha you can find from here 90 minus theta, or you can find here from here the theta value. Theta is equal to 90 minus alpha. Now put value of theta here. So the torque will become mv cos 90 minus alpha. Cos 90 minus alpha is equal to sine alpha. Sine alpha. So finally your torque will be mv sine alpha. And what is alpha? Alpha is the angle between the magnetic moment and the magnetic field. Magnetic moment and the magnetic field. Okay, note down this. This derivation is little bit complicated, but you will first use this formula in the direction, and accordingly you will do this. Note down this. So in the next class, we will finish this chapter. Both of you writing, Matthew and Nafisa?
Yes, sir, yeah.
Yes.
When completed, ask me to scroll down.
So can you scroll down?
Nafisa, should I scroll down?
Yes, sir. Yes, sir.
Just add this also. Line of action same, line of action is different for the non-collinear force. Scroll down. Matthew, scroll down.
1 second, sir.
So you have to remember this formula: force torque is equal to force into perpendicular distance from the axis of rotation. Here I am adding both the torque because both the torques try to rotate the coil in the clockwise direction.
Just take a scroll.
And this thing I have taken from this here. Okay, this is AD. FAD is acting like this, and FBC is acting like this, and this is the length P. Okay, I have joined like this. I have shown here with the forces, how the forces are acting.
Done, sir.
This is the tau, and this is tau representing here the total torque on the coil. Magnetic moment is equal to NIA. N is equal to 1 because we are calculating the torque for N equal to 1. So, magnetic moment for N equal to 1. Number of turn in the coils we have 1.
Done, sir.
Nafisa, completed?
Yes, sir. Yes, sir.
So finally you will get this formula. You should learn this formula. Torque on a current carrying coil is magnetic moment of the coil and the magnetic field in which the coil is placed, and sine alpha. And alpha is the angle between the magnetic moment and the magnetic field. Magnetic moment will always be perpendicular to the plane of the coil. And in the next class, we will finish this chapter. There is one more topic, moving coil galvanometer. After that, this chapter will be finished. Completed?
Yes, sir.
Matthew completed?
1 second.
So this formula, this is the torque. Tau is the torque here. Torque on coil. Given by magnetic moment of the coil, magnetic field in which the coil is placed, and sine alpha. Alpha is the angle between the magnetic moment and the magnetic field. This you
Yes,
can
sir.
see from you can see from this diagram also. If you have any confusion, so this derivation is For this derivation, you have to practice this at least 2 times and try to do this derivation by yourself. And if you are not getting the direction and all that, when you will try it by yourself, then definitely you will get how the direction of the AV force is this, how the direction of the force is CD is this. Okay. I am just applying the rules that I have already told you. So I am applying the right